This is Fundamental Problem 34 from Chapter 12. The platform is rotating about the vertical axis such that at any instant its angular position is theta is equal to 4 times t to the 3/2 in radians, where t is in seconds. A ball rolls outward along the radial groove so that its position is r is equal to 0.1 times t cubed in meters when t is in seconds. Determine the magnitudes of the velocity and the acceleration of the ball when t is equal to 1.5 seconds, and this blue curved arrow here is showing you the positive direction for theta dot and theta double dot. Okay, so from equation 1231, I can write the velocity in polar coordinates. From equation 1232, I can write the acceleration in polar coordinates. What I'm looking for, determine the magnitudes of the velocity and the acceleration. Okay, so I need the magnitude, so I need the radial component and the transverse component, and the radial component for the acceleration, the transverse component, and then I can use that to find the magnitudes of the velocity and the acceleration. I'm doing this when t is equal to 1.5 seconds. If I look at everything that I need in order to find the components, I'm going to need r dot, I'm going to need r double dot, and I'm going to need r itself. So I need r dot, r double dot, and for all of those I want to evaluate when t is equal to 1.5 seconds. I don't actually need theta, but I do need theta dot and theta double dot. Okay, so you have an equation for theta here and an equation for r here. I'd like you to find everything here, r dot, r double dot, theta dot, and theta double dot when t is equal to 1.5 seconds. So you can pause the video now and do that. Okay, so we start off with r, which is 0.1 times t cubed. If we take a time derivative of that, we get 0.3 times t squared. Taking a time derivative of that gives us 0.6 times t. We evaluate each of these when time is equal to 1.5 seconds, and we get 0.3375 for r, 0.675 for r dot, and 0.9 for r double dot, and I've left off the units there, but it would be meters, meters per second, and meters per second squared. We have theta here. Taking a time derivative gives us 6 times t to the 1/2. When t is equal to 1.5 seconds, we get 7.348 radians per second. Taking a time derivative of 6 times t to the 1/2 gives us 3 divided by t to the 1/2, evaluated when t is 1.5 seconds. That gives us 2.449 radians per second squared. Now I want to find the radial component for the velocity, which is just r dot. So that is 0.675. I need the transverse component, which is r times theta dot. R is 0.3375, and theta dot is 7.348, and that gives me 2.48. So for the magnitude of the velocity, I have the square root of 0.675 squared plus 2.48 squared, and that gives me 2.57 with units of meters per second. For the acceleration, I need r double dot minus r times theta dot squared, so that's 0.9 minus r is 0.3375 times theta dot squared, so that's 7.348 squared, and that gives me negative 17.3. This was the radial component of the acceleration. I need the transverse component, which is r theta double dot plus 2 r dot theta dot. R is 0.3375. Theta double dot is 2.449 plus 2 times r dot, which is 0.675, times theta dot, which is 7.348. And that gives me 10.75, Then for the magnitude of the acceleration, that is the square root of negative 17.3 squared plus 10.75 squared, and that gives me 20.4 with units of meters per second squared for the magnitude of the acceleration. I would just like to say one thing before we finish here. If you remember when we did uniform circular motion back in Physics 161, if you have something moving in a circle, in order for it to move in a circle, you have to have a net force pointing towards the center of the circle. And remember, the sum of the forces in the radial direction is equal to the mass times the acceleration in the radial direction. So if you have to have a net force pointing in towards the center of the circle, in order for an object to move in a circle, then you have to have an acceleration pointing in towards the center of the circle. And because outward is the positive radial direction, the radial component is going to be negative, and you would have to have a negative component for the radial component of the acceleration as long as something is moving in a circle. If you were swinging something around in a circle on the end of a string and then you let go of the string, you're no longer providing a force towards the center of the circle, and the object is going to stop moving in a circle and fly off in the tangential direction when you let go of the string. So we should expect to have a negative sign here.